Welcome to Study Loop.
A current-carrying inductor has a magnetic field inside of itself and hence stores magnetic energy. So the magnetic field inside a solenoid B is equal to mu naught N I, where N is the number of turns per unit length and I is the current flowing through the solenoid. And this we know the values for, so we can calculate the magnetic field. That's 4 pi times 10 to the minus 7 in SI units, mu naught. Number of turns per unit length is 400, or the total number of turns is 400, and the current is 80 amperes, so we suppress the units. And the total length of the solenoid is 0.25 meters, so 400 over 0.25 is small n, the number of turns per unit length. And hence we get a magnetic field inside the coil to be 0.161 Teslas. Next, we wish to calculate the energy density in the magnetic field. So the energy density stored in the magnetic field, small u, is equal to B squared divided by 2 times mu naught. And now we can calculate this value. So the magnetic field, we calculate it to be 0.161 Teslas, and that's squared, over 2 times mu naught, which is 4 pi times 10 to the minus 7 Tesla meter per ampere. And we suppress the units again, and we get that the energy density, little u, is equal to 1.03 times 10 to the 4 joules per cubic meter. Next, we'd like to calculate the total energy stored, U, capital U. And capital U is simply little u, the energy per unit volume, times the volume of the solenoid. And this is simply the energy density times the length of the solenoid multiplied by the cross-sectional area. And these values are not all known. So that's U is 1.03 times 10 to the 4 joules per cubic meter. The length of the solenoid we know is 0.25 meters, and its cross-sectional area is 0.5 times 10 to the minus 4 meters squared. And hence we get the total energy stored in the magnetic field to be 0.129 joules. Finally, we want to find the inductance L. And since we know that U is equal to a half L I squared, we can rearrange and solve for the inductance L. And L is simply 2 times the total energy stored divided by square of the current through the solenoid. And this is equal to 2 times the energy we calculated, 0.129 joules, divided by 80 amperes, and that's squared. And hence we get the inductance of the solenoid to be 4.02 times 10 to the minus 5 henries.